Thank you very much for the flattering introduction, Jules. Yes, I'm going to dig deeper into how to actually build structured streaming applications, how as an end user should think about constructing your applications and making it ready for production. So, but for those who are not familiar with what structured streaming is all about, why we built it, let me start from the basics. And the basic truth of the matter is building robust streaming applications is really hard, because there are a lot of complexities that one needs to consider, one needs to solve before you can actually put a streaming application in production. To start with, data can be very complex. You have tons of different formats the streaming data can be in. You can have JSON, you can have Abro, you can have arbitrary binary, and you have to deal with all of these formats as a first step before you can actually start doing any sort of processing on it. And then this data can be dirty. Your data may have missing fields or randomly corrupted, and your data can be late and out of order. You have to deal with all of that and still reason about what's going on, what is the semantics that you're getting. Then your workloads can be very complex. And I really don't need to elaborate too much on this, but two very key points that makes workloads complex is, one is event-time processing, where you actually want to use the time embedded in the data itself to do complex CEP-style processing. And then, as Matti already talked about in his keynote, that streaming applications don't actually work in isolation. For a real production-grade application, it usually involves combining it with other kind of workloads like interactive queries, batch workloads, machine learning on top of streaming, etc. And together, all of this, you have to make sure that you can reason about the semantics of the application, of the continuous application as a whole, and which is very hard. And then the third thing is that systems are complex as well. Streaming applications may need to interact with both streaming storage systems as well as batch storage systems, and batch storage systems can be arbitrary SQL, NoSQL, file formats, Parquet, ORC, etc. There's a crazy world out there. And you have to deal with also system failures. It's a distributed system, right? Random things can fail at some point of time, but you still have to give end-to-end guarantees, because otherwise, if you cannot reason about the end result that you see, you're in deep trouble. So structured streaming was designed to solve all of these complexities. In a single slide, what it is essentially a stream processing engine built on top of our Spark SQL engine, which makes it fast, scalable, and fault tolerant. It provides rich, unified, high-level APIs to deal with the complex data and the complex workloads. We will elaborate on that in the rest of my presentation. And Spark automatically comes with a very rich and growing ecosystem of data sources, which allows you to integrate your streaming applications with a very growing number of storage systems, both batch and streaming. And we build this with the single philosophy that the simplest way to perform stream processing is to not have to reason about streaming at all. You should, as an end user, you shouldn't have to reason about what happens when the data is late, what happens if system fails, what happens when things come out of order. You shouldn't have to reason about any of that. The system should automatically take care of that and give you the final correct result. And that's all the user should care about. And to do this, what we have done is that we have defined a new model, a new way to treat streams. And the way we propose is to treat streams as nothing but tables, except this table is unbounded. So as new data is coming into the stream, they are like new rows being appended to this table. Essentially, it's an append-only unbounded table. That's a conceptual model to think about. And now what makes this very easy is that it unifies both batch data and streaming data by this single concept of tables. And that leads to our new model of how to see stream processing in terms of tables. So let's say you have an input stream, which you can define as a conceptual input table that every time you see that input table, it's growing in size. So if, let's say, every trigger interval of 1 second, you see the table, it is growing continuously in size. And now you can define your usual queries on top of this table, and what you get is essentially a result table, which is also changing in size, changing in content as new data is getting added to the input table. But ultimately, you really care about what gets written to an external storage, not what the conceptual result table is. What gets written, how do you take the changes in the result table and write it to an external system, like some file system or SQL or NoSQL. And that is defined by the output. For example, if you want to write the whole table every time, because pretty much your whole table changes every time there is some input, then you can define the complete output mode, where the whole table will get written to some SQL, NoSQL, or file system. But in some cases, you may want only the new rows added to the result table to be written out every time, and that would give rise to the append output mode. There are other output modes. I'm not going to go into that level of detail now, but I hope you get the high-level idea that this is the new model we're proposing, and we basically look to streams in terms of tables as a conceptual table, which is unbounded and continuously growing. In actual execution, we don't keep the unbounded table. We incrementalize the query to do in a smart way, and I'm going to talk about that later. But what this allows you is that you can now have a single API for the Dataset DataFrame API to deal with both static tables and unbounded tables. So if, for example, if you want to write a batch query using data frames, you'll have this sort of a simple code where you're reading from JSON, you're doing some selecting, filtering on it, and then writing it out to Parquet. Now, this works in batch data. To convert it to work on streaming data where you have JSON files coming in a directory, all you need to change is change read to read stream and write to write stream. And this will automatically start reading JSON files added to a directory and start appending it to a Parquet table. But the key thing is that your actual query, your business logic does not change. Your code does not change. So you can write your business logic once and then either apply it to batch data or streaming data without having to change a single line of your business logic code. And internally, what the Spark SQL engine would do is that take this data frame code and convert it to a logical plan which expresses what is your intent, what do you want to compute. And then from this logical plan, the Spark SQL planner will essentially construct a series of incremental execution plans. Each of these execution plans will take new data that has arrived since the last time and do whatever processing it needs to do using the incremental form of your query and write it out as Parquet files. And so essentially what Spark SQL is doing is converting your batch-like query to automatically incrementalize it and so that it operates on batches of new data. And while it's doing that, it automatically takes care of fault tolerance using checkpointing. So every incremental execution, what it does is it writes the metadata of the range of data it is reading into a write-ahead log. And so and the system, whenever it fails, if there is any failure, it can automatically read that write-ahead log and reconstruct what needs to be reread and reprocessed. And the streaming sources and sinks are designed to automatically replay the exact range of data that needs to be reprocessed in case of failure and ultimately dedupe the output results so that you get end-to-end exactly one's guarantee. The end user doesn't need to reason or think about any of the failures and stuff. Now, this was a very simple example. Let me actually go deeper to actually a more realistic use case of a complex streaming ETL use case example. Now, traditionally, ETL has been done in a following fashion, where you have raw, dirty, semi-structured, or completely unstructured data coming in through streams. That is usually dumped as fast as possible in raw files. And then a periodic job every hour or every 6 hours takes those raw file dumps and converts it into structured data that is presented as table for more further advanced analytics. Now, the problem with this method is that this incurs hours of delay between when the data arrives into the system and when the data is ready for doing complex analytics. This is often unacceptable when you need to take decisions on the data as soon as possible. For example, intrusion detections, anomaly detection, whatever Michael demoed that you want to know what is going on in your AWS account. Is there any attack going on right now? You want to take decisions on that as fast as possible, but this doesn't allow that. But with streaming ETL using structured streaming, it bypasses this intermediate step and makes data available in structured form within seconds. Let's see how. So here's an example. Let's say you have data coming through Kafka. It is formatted as JSON. You need to parse that JSON. You need to unnest it because it's very nested, which most JSON data are. You need to flatten it. You need to do some data munging on it. And finally, you want to store it as a structured Parquet table. And you want to get end-to-end failure guarantees in this whole process. All the code that you need to write is just this. You get all of this nested parsing and everything in just this much piece of code. Let me actually walk through the code so that you understand what each steps are and how to think about when you have to write your own structured streaming app. So the step one is you have to read from Kafka. And since Spark 2.1, we have added the Kafka as a data source. And to configure it, it's very easy to configure. You have to specify how to read the data by specifying Kafka the Bootstrap servers. Usual Kafka consumer configurations totally work in this Kafka source. You need to specify what to read. So either you subscribe from a fixed list of topics or a dynamic list of topics using a regular expression or a specific set of partitions. Again, the same set of operations you can do on a Kafka consumer. And where to start reading from. Either you want to read from the latest point in the Kafka or from the earliest point or from a specific partition offset. But what this code now returns is a data frame which has the following columns. It has the key and the value in the binary form. And it has a topic, partition, the offset of that record in Kafka, and the timestamp when the Kafka timestamp when that record came into Kafka. And now you have these columns, and now you're free to select and pick what data you want to use out of this. It is already structured for you to do further processing on. So the next step is actually parsing the JSON and stuff. So now the payload is actually binary format. The first step is actually to convert it into string. And so you can cast it as a string, and then comes the complicated part of actually parsing it to JSON. And for that, we have added in Spark 2.1 a very easy but very powerful API called FromJSON. This FromJSON function takes any arbitrary JSON as a string, and given the schema, it actually parses it and automatically converts it into columns. So from the JSON column, it can automatically parse it and forms a nested data column with each of the JSON fields becoming a separate column. And now you can go ahead and unnest it very easily, flatten it to be separate unnested columns. And now it's ready, it's flattened, it's simplified, it's more structured. Now I can write it out to Parquet. And writing it out to Parquet is pretty easy. You can very easily specify the format, which is Parquet, and the destination, and you can partition the files by date. And this is important because later you may want to actually query time slices of the data. For example, what happened in the last 12 hours or 40 hours. So you can already partition the Parquet table by time and date, and that's it. And then the next step is you can enable checkpointing just by specifying the checkpoint location, which HDFS S3 or S3 directory where you want to write the system to write the offset to. And that's it. Next you call start, and what it results in is the system actually starting a continuously running streaming query. It will keep running in the Spark cluster for as long as the cluster is up, and internally it will do all the incremental execution that keeps reading data from Kafka and writing out to Parquet. And what this code returns is essentially a handle to that continuously running incremental execution with which you can either monitor or manage the query, start it, stop it, etc. So what this enabled you is that the data from Kafka is immediately available in Parquet as structured form within seconds, and the users can start writing complex ad hoc queries on the latest up to the second data from the Parquet file immediately. And the very cool thing, and which makes structured streaming different from pretty much all other streaming systems out there, is that it guarantees that even though the whole system is distributed, a part of the system can fail or the whole system can fail, when you're querying the Parquet table, you get the guarantee that you either get all the updates in the Parquet table or you don't get any of the updates because there was some failure. You don't get any sort of data inconsistency. And so whenever you're querying this Parquet table now, you are guaranteed to get a consistent view of the data that has arrived till now. We call this property prefix integrity. I'm not going to go into any more detail about that. You should read up our blog where we have discussed prefix integrity in much more detail and how it is different from other streaming systems. Okay, so this was still a relatively simple use case. It is generally a complex use case, but I've shown that how it becomes easy with structured streaming. Let's look at further advanced streaming analytics. And then one of the important ones is event time aggregation. You want to use the data present. You want to use the time present in the data to do further aggregations like windowed aggregates. For example, how many errors were there in the last 1 hour, every hour over the last 5 days, etc. And this is one use case that was where dstream kind of was insufficient because it was not designed keeping event time in mind, and which is why we built structured streaming in the right way. And so structured streaming makes it easy because windowing is just another type of grouping now. So if you want to do something like count the number of records every hour, it's very easy. You just say group by. We have this new operator called window, and you specify what is the column to read the timestamp from. And this column can be any column in the data frame after you have done all the processing, all the complex transformations you may need to do to convert the timestamp from epoch time to correct format or back and forth, get the time zone right. After doing all of that, the final timestamp column you can define the window on. And you can just say, I want window by 1 hour. Or you can actually group by both time window as well as some other column. For example, let's say you want to do the average signal strength of some devices every 10 minutes. Then it's, again, just two operations in the group by, both device and the window. So this kind of seamlessly simplifies event time aggregation in the same API as the existing group by and stuff. And if you have complex aggregations, the usual user-defined aggregates are automatically supported in this API. But what happens underneath is actually far more complex. To do this running aggregations, you need to maintain state across the batches of data that you're processing in each incremental execution. So this is a distributed state, and it needs to be saved in a fault-tolerant manner, and Spark SQL handles it automatically. So this state is each trigger essentially reads the state from the previous trigger and outputs the updated state for the next trigger to use. And this state is essentially stored in memory while it is being backed by a write-ahead log in HDFS and S3. This is the current implementation. And what this guarantees is that even any stateful transformation, not just aggregation, has full fault tolerance end-to-end exactly once guarantees. But this state cannot grow indefinitely. You cannot keep state intermediate aggregate as state for last 1 year because you have limit on how much memory you have in your system and stuff. So you need to be able to expire old state. And that's what we have, and that's why we have introduced watermarking in Spark 2.1 so that we can handle we can limit the amount of state and as well as handle late data. And the way this works is as follows. The watermark is defined as a boundary, a continuously advancing boundary that is trailing behind the max event time that the system has seen in the data. So if the blue line is the max event time that the system has seen till now, let's say, then watermark is a boundary that is trailing behind it in terms of event time. And any state that is older than that watermark will be dropped. Now this gap between the max event time and the watermark is configurable by the user. And what this allows the user is to specify how late the data can be, because any data that arrives before the watermark, or it is later, it is newer than the watermark, that can be late, but it is still allowed to be aggregated. But any data that is older than the watermark will be dropped because its corresponding state has already been removed in an attempt to clear off old state, because to limit the amount of state the system can have. And so what this allows is for the user to configure, because the trade-off between how much late data to allow versus how much in-memory state to keep. And to do this programmatically, it's very easy. All you need to specify this additional thing with watermark. What is the column to do, on which the watermark is to be defined, and what is that gap? And then the system will automatically figure out that when data is coming in. For example, here the vertical axis is the event time, and you have these data points in yellow dots. When there is data coming in with different event times, the system automatically figures out what is the max event time seen till now. And based on its what it tracks, it automatically defines what the watermark should be with the 10-minute gap. And based on that, it keeps figuring out that for every further data point, whether it is late, but later than the watermark, it is allowed to aggregate, or if it is too late, then it is dropped because its state has already been cleared. This is all automatically handled by the system, so the end user does not have to reason about what happens when there is late data. As long as you configure your late threshold correctly, your data is guaranteed to be processed, and your results guaranteed to be correct within those constraints. So this was one example of stateful stream processing, where you're aggregating, but you may want to do further arbitrary stateful aggregation. For example, let's say you want to track user sessions. That is a case of sessionizations where you want to track every action taken by the user, and you want to automatically model the user behavior and stuff. And for that, we have added recently, actually as of yesterday, map groups with state. It is for those who have used dstream.map with state, this is exactly the same idea, where you just specify for each of your event how to take the previous state and update the state for every event. And this state is per key. You just specify that, and the system will automatically take care of applying that function on all the data for every key and maintain the state in a fault-tolerant manner and stuff. So the current API is for Scala and Java, because we have designed it to be for type-safe languages, because we have observed that most people want to write these sort of complex functions in type-safe languages. So we have added it for Scala and Java only right now, but depending on demand, we might add stuff for Python as well. Anyways, I don't have time to cover all the cool stuff we have been doing. In fact, we have been doing a lot of stuff. This has been a really fast-moving project inside Databricks. And things that we have added already and are going to add are, here's a sneak peek, is we have added very strong APIs for monitoring your streams, like the streaming query listener, where you can get periodic heartbeats on how your stream is progressing, so for doing health and performance monitoring. And in Michael's demo, you saw the processing rate graphs and how long it took to process each batch. That is using this exact same API, and it's automatically integrated as part of the Databricks platform. We have also added the ability to do batch queries on Kafka, so you can treat Kafka pretty much like a file system. We are going to add in 2.2 a Kafka sync, so they can directly write out to Kafka as easily as writing out to a file system, but with the caveat that since Kafka doesn't support transactional writes, it doesn't quite give exactly one's guarantee. You get at least one's guarantee, but that's a Kafka limitation. And then we also added an update output mode where you can write only the rows in the result table that has been updated to an external storage. And so all of these and more are coming in structured streaming. We will keep you posted. And the way we communicate this is through our blogs and the programming guide. So all the contents of this slide is essentially presented in a more written and more detailed format in the programming guide. You should go really take a look before you start writing structured streaming apps. And there are deeper dives into each of the topics in our blog post, so stay tuned on our blog post. In fact, we already have a few out there. You should really go take a read. And here is a sneak peek. So if you are wondering how does it compare with other engines, we have this elaborate table, just like all projects have. But to understand this table, you really should take a look at our blog, and that's where you would understand why this prefix integrity is important and how it separates us from other streaming engines. Anyways, you probably have a lot of questions to ask. So we have a bunch of office hours. I have office hours today and tomorrow. Michael has one in the afternoon today. Come to me, come to Michael, and ask us all the hard structure streaming questions so that we can learn from you and you can learn from us. That's my last slide. Thank you very much.
Thank you, guys. Thank you, TD, for actually giving us an insight. Everything we saw this morning seems so easy, but this is actually what's under the hood that actually makes it so easy to write structured streaming. We've got 4 minutes. We've got 2 mics on either side of the aisle. If you have any questions, please ask now, or if you don't have any questions, maybe you can just come back to the office hours and ask TD. So this is the right time. We got 4 minutes. Let's go.
A question? So this is a tough high-level question, but what is the fundamental difference between these incremental logical plans for the queries and my regular logical plan? This statefulness, is there any other complexities that are?
So the biggest difference is the stateful one. So the standard batch logical plan doesn't have a concept of state, right? There is no prior state. Each batch query is independent of each other. But in streaming, you have to take the state into account. And so for aggregations, for map group with state, so that is one of the fundamental differences between a streaming logical plan or a streaming incremental execution plan versus other plans. There are a few other minor differences, like there are some operations that are very hard to incrementalize. And that, so there are operators that are allowed in the batch plan, but not yet supported in the streaming plan because they're incrementally they're incredibly hard to incrementalize. For example, deduping and stuff. We're working on it, but a true deduping requires keeping all the prior data from the stream to be available, which is not feasible. So that is something not yet supported. So those are the differences between a streaming and a batch logical plan.
Thank you.
OK, go for it.
So when you have something like from JSON, how do you handle schema evolution when new fields are added?
That's a very good question, and it is a very hard problem. So as of now, what we have done is that whenever you have to specify a streaming source, let's say you want to read a bunch of JSON files, you have to specify the schema from before. So that if there is any sudden schema break in your data, you immediately find it in your app by the app will start producing nulls or will crash or something, and then you can actually actively go and actually modify it and make it more generic so that it supports schema evolution. So, but at least what we have with this, what we have done is that we do not hide any error, and which is the worst thing that the system can do is hide these errors that comes from schema evolution and stuff. We at least expose them, and then the user has full control on how to make it more future compliant, future ready and stuff.
Thank you.
Lady, go ahead.
Hello, thank you. So quick question on Streaming Query Listener. We were testing that in December. Pretty common use case of just iterating through files on S3. Everything was working great. We loved it. But we got blocked because we couldn't figure out which files had actually been read. Like in the listener, we were unable to see, okay, I've read, because we're basically trying to make sure that our application was going through files fast enough to meet our SLA.
Very good question, and wow, people are already using structured streaming apps.
That's what we want.
Thank you. That's awesome. So yes, the progress list, the way our file format, our file sources are constructed is that we don't expose the list of files in this listener because the list of files can be so huge, it can bog everything down. So in that case, if you really want the list of files, we have to do a little bit of deeper digging behind the scenes. So for the file source, what we do is we maintain a separate file source level log on which files are present in each batch. It is present in the same checkpoint location. So if you actually look through the directory where the checkpoint is being saved, you can actually find out that log. That log is actually essentially formatted as JSON, so that these log files are future-proof, so that we can, across Spark versions, we can always restart queries and stuff, so it's future-proof since Spark 2.1. So you could look at those. There are no APIs for that yet. You could look at those and find in each batch which are the files present.
That's fantastic. Thank you. And,
All right, thank
once
you. We don't
know
have
that,
time
we
for
can archive it
questions.
and we're good.
Give a big hand to TD. Thanks a lot, TD.
Thank you very much, guys.